Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
All right, everyone. So it's a pleasure to introduce Vijay Pedinti today. I think everyone here knows Vijay. Vijay was a STAR intern here working with Mike, and he's a STAR student at Johns Hopkins University, where recently he won the Best Paper Award at last year's Interspeech and turned in the winning system for the Aspire Challenge last year. So he's got this long record of super successes, and he's going to tell us today about some of the technology behind them.
Good morning, everyone. At the Johns Hopkins University, I work with Dan Pove and Sanjeev Kudanpur, and most of this work was done in combination with them. So today I'm just going to talk about multi-rate neural networks, which I'll try to convince you are very good for very efficient acoustic modeling. And these become important in the current scenario where we have a lot of data and not enough time to model on this data. So before I start with the actual talk, I would like to motivate the research goals behind pursuing this current line of work. So I basically concentrate on what is called distortion stable sequence recognition problem. So for the sequence recognition part of this work, we basically use models which are capable of tackling long-term or long-span temporal dependencies in acoustic data, which would be any model like a LSTM or a BLSTM or any such model. And for the distortion stable part, we basically rely on training data to be very representative of the possible operating scenarios in which the model is going to be used. This essentially means that in most of the cases, we have an immense amount of training data, and we are faced with the challenge of reducing the training time and also the decode time, because if the models get really huge, it's going to be a really big problem in terms of latency during decode. So in order to reduce the training time, there are several different techniques. So one of them is to just use a distributed optimization algorithm. But it turns out that even with distributed optimization, if each of your instances can operate at a really fast speed, you do get significant speedups. And that's the part I'm going to concentrate on. And the models which are capable of fast training and for really low latency decoding are our main research focus. And I'll try to convince you during the course of this talk that multi-rate neural networks are a really good solution for these problems. So the outline of the talk is going to be like this. I'll be initially discussing the problem. Then I'll discuss few of the current approaches used to tackle this problem, which belong to two different classes, which are feature-based approaches and some model-based approaches. And then I'll actually introduce the multi-rate idea, and I'll show the application of this idea in both convolutional neural networks and recurrent architectures. But most of the results right now are just on the convolutional architecture part of it. So what exactly is the issue in sequence recognition? So there are a variety of reasons. You have long span dependencies in input sequences like a sequence of speech vectors. And the reason for that is the inherent way in which speech is being generated, which is by an articulatory system which has physical constraints. So there cannot be rapid switches between different articulatory states. So you have the co-articulation effects where speech across a wide window is getting influenced by speech sounds from a different phoneme across several different time steps. And you also have reasons like reverberation, which are environmental reasons, where you have delayed versions and scaled versions of the speech signal adding up to the actual speech signal being recorded at the microphone. And finally, you have various kinds of channel distortions where the effects can actually be non-linear. And in some cases, adversarial cases like speech encryption, you actually have frequency scrambling techniques where these distortions can be quite severe. So in order to tackle all these problems, we need to design models which are going to remain stable to any of these distortions. So during the past 2 decades, there have been a variety of approaches towards this problem, and most of these approaches can be classified as feature-based approaches. So in these approaches, people quickly realize that you cannot just splice a large chunk of speech frames, dump them into your acoustic model, and just hope that your acoustic model is going to learn the necessary transforms. And the reason for that is as you increase the sequence of your feature vector, you have increased variance in the input representation, which is inherent. And in addition to that, because of additional nonlinear temporal warping that happens in speech, this variance increases further. So in order to learn transforms which are invariant to such highly variant input representations, you need a lot of data. And later on, I'll show you that irrespective of the amount of data, it's always going to be a problem. So initially, the approach towards this was to design representation functions which are going to guarantee some form of stability to a variety of temporal distortions. And this stability is usually defined as Lipschitz continuity of the feature transform. And some of the most widely used approaches which follow this particular line of thought are what are termed as multiscale feature representations. So in multiscale feature representations, you basically are analyzing features at several different resolutions. As soon as you have a low resolution feature stream, this low resolution feature stream is going to remain stable to local distortions in the input pattern. But the problem with this really low resolution feature streams is that it also discards a lot of information which would be very important for classification. So people try to solve this problem by building acoustic models which operate on different feature streams and trying to combine the judgments from these acoustic models using a variety of techniques. So for example, if you try, so these are two different, these two plots are generated by two different multi-resolution techniques. The first one is a simple Gabor filter based approach. So over here, if you look on the plot over here, so you have 3 different plots over here, and the first one is the really coarse feature, and you can imagine that any kind of temporal shift in the acoustic events over here or frequency shift is not going to influence that impact that representation to a great extent. On the other hand, you have 2 different kinds of very fine resolution in terms of frequency over here, and any shift in the acoustic event over here is going to immediately show up in this representation. So if you have an acoustic model which is looking at all these representations simultaneously, or a bag of acoustic models which are looking at these representations, you can hope to both be stable to distortions while preserving information necessary, finer resolution information necessary. So this was one particular, so over here we are basically taking the input representation and passing it through a filter bank which has filters with different resolutions. This has also been done in a different way, where instead of using a filter bank, you basically use a hierarchy of filters or what's called a wavelet, and you get a different style of representation. But the critical idea over here is basically decompose your representation into multiple resolutions. In addition to this, there are also other kinds of techniques in order to capture this long-term information in the acoustic signal. And one of the really important techniques which has been shown to be very influential for adaptation is what we call permutation invariant representations. So these are representations which do not preserve any information about the actual sequence of data, but they capture long-term stationary information in the speech signal, like say the speaker characteristics or the environmental characteristics. And this kind of information which is giving us long-term detail is very popularly used as I vectors or mean noise estimates. But there is an alternate approach in order to tackle the same problem of long-term sequence modeling, and which is the model-based approach. So how exactly do model-based approaches deal with this problem? So the model-based approaches assume that you just have a sequence of short-term instantaneous representations, which is something you see in an MSCC feature vector sequence. And given that you have this sequence of short-term representations, you are trying to model the long-term temporal dynamics. And we already know that we cannot basically splice a long window and dump it into the DNN. So in order to tackle this problem, most of the effective models basically learn temporally local transforms. So each transform is always just looking at a finite chunk of feature sequence, but neural network as such is able to process information from a wider context. And there are two strategies to achieve this. So if you are using a convolutional architecture, you can basically do hierarchical filtering. So you can stack a series of convolutional layers, and each time you go deeper into the network, you see a wider context. But because this wider context has gone through a layer of filtering, its resolution has reduced to a certain extent because of pooling and other things. So you're basically, the network as a whole is looking at a wider context, but each transform is temporally local or looking at a lower resolution representation. On the other hand, you can deal with this problem in the recurrent architectures, where when you are learning a transform on the input, it's temporally local, but the long-term information is being captured in the state of the vector. And this state can be derived using a task-dependent loss function, so it will preserve the necessary detail if we are able to train it in the right way. So I'll be talking about, so we are interested in these two kinds of architectures. And in both these architectures, there is this additional detail that not only the transforms are temporally local, but they're also tied across time steps. So even if you look in a convolutional architecture or in a recurrent architecture, the same transform is being used across time steps. And this shared statistical strength ensures that you are learning better transforms compared to a simple DNN-based approach. So because recurrent architectures are so popular popularly used in tackling this problem, let's just initially look at the recurrent architectures. So if you are just taking a simple RNN, which doesn't have any frills, it has several problems, and one of which is basically limited memory. So it's not able to memorize a lot of detail in the past, and it also has problems of vanishing and exploding gradients. So in order to deal with these issues, several different kinds of architectural variants are proposed. But despite the use of these architectural variants, RNNs have this very basic problem where the loss function that we use to train the RNN cannot be computed parallelly. That is, if you are computing the outputs of an RNN, all these outputs cannot be computed parallelly, and they have to be evaluated sequentially. So in order to overcome this problem, people normally use batching of sequences. So they basically predict the loss function from several different sequences in parallel. But despite the use of all these tricks, the fastest feed-forward networks are always faster than an RNN. So this is the reason we decided to approach the sequence modeling problem, initially using convolutional architectures. Sorry.
Why does it necessitate the sequential processing of the outputs as opposed to just the hidden state vector? Like, couldn't you?
So I just mean the hidden state as the output of the network.
Yeah, okay.
Not the actual posterior.
Outputs. Okay.
So in order to tackle that problem, we actually wanted to explore convolutional architectures, and we wanted to make sure that the convolutional architectures were not sufficient for sequence modeling before we shift to the RNN architectures. So as I described before, convolutional architectures have a variety of advantages, where the main advantage over here is that if you have the hidden activations at different time steps at a particular layer, all these activations can be computed parallelly, which is going to give you a huge speed advantage during training. But the problem over here is if you want to increase the context of the network, you both have to compute more hops in your unrolled convolution, and at the same time, the network as a whole would have to process this wider context information. So there is going to be a linear increase in the number of parameters, and also a linear increase in the computational cost as soon as you come to convolutional architectures. So a very simple way to deal with this problem is basically use subsampling. So essentially, we are not computing all outputs at any given layer, but just few of them. So you can think of it like this. If you have a filter with a fixed context, and if you are not computing every output in the input at the input context of the filter, basically the input dimension of that particular transform reduces, and essentially reduces the number of parameters. And also, because you are not computing everything in the convolutional layer, you have a speed advantage. And this is nothing new, and people normally use this uniform subsampling strategy, where they hop their filter by a specified width, and it is popularly used in all the CNN architectures. But what we want to achieve is a subsampling which is far more severe than what you have from a uniform subsampling strategy. So there have been other explorations of non-uniform subsampling strategies, and these were previously done in hierarchical neural networks, where you have two independent neural networks cascaded, but both of them are trained independently. So, or here you have the advantage of actually decoding the output of a lower level neural network, looking at the individual frames and deciding which of them are important and which of these frames are not so important. So one of the strategies people used was basically run a first pass decode or the output of the lower level neural network and just select one frame per every context dependent state that you have. But in our case, the problem is that we have a normal DNN where every layer is decoded, trained jointly. So you cannot assume to have any understanding of importance ahead of time. So in order to come up with a non-uniform subsampling strategy in this particular case, we designed our problem like this. So given a desired context that we want to model, which is a TL represented by TL, TR over there, and the number of convolution layers that I want. So the number of convolution layers is the number of sequential operations that are going to happen in your network, which will limit your speed. Choose the filter context, that is the context of the transform at each individual layer, and the time steps at which these convolutions have to be performed. And because we had no idea of how these had to be done, we came up with a criteria, and the criteria was we want to ensure the propagation of all the information from the input sequence when we are trying to compute one single output. And we wanted to test out that if we design a network which satisfies this criteria, are we going to take a performance hit in terms of the convolution neural network performance. So there are several ways to find a path from the lower level sequence to the output sequence while ensuring that we have minimum activations. But we also have this other constraint, if you remember, that our convolution layers have to be always temporally local or operate on a lower resolution information. So this gives us another constraint that as we go deeper into the network, we are going to increase the context of the network. So it turns out that if we just linearly increase the context of the network and basically just evaluate the outputs at the edges of the filter. So in this particular diagram, you can see that previously if you had a normal convolutional network, you would have computed every output at each layer, and that would have meant so many computations, which are represented by every lines of all colors, including black. But if you are using the current subsampling strategy, you would just compute the colored lines, non-black lines, at each layer. And you can see the drastic reduction in terms of computation. So, yeah.
I guess I have two questions. Well, let me start with the more interesting one. So do you think you could get an effect similar to dropout by having say two different window lengths at each level? So here, the orange nodes are taking two inputs, and every orange node has exactly two inputs. So there's a filter that takes two things. At that same level, do you think you could say, flip a coin, say I'll have a window that also takes 5 inputs instead of 2, 5. And when you get to a node that you've selected to compute its value for, at that point you flip a coin and you say, will I use the filter that takes 2 inputs or will I use the filter that takes 5 inputs? And you did that at every level. You'd essentially be training over multiple architectures. Do you think that would be analogous to dropout, or that it would increase the robustness in a similar way?
It would definitely be analogous to dropout, where you have multiple filters in your CNN at that particular level. But it would essentially increase the computational cost. And
Because you're either...
you either have a 2-input filter or a 5-input filter.
Actually, it wouldn't increase the computational cost because it would double the number of parameters, but at each node that you select to evaluate, you either use one filter or the other filter.
If you have a wider filter, you would also, so in this particular case, when I want to compute the output at one particular frame, in a frame randomized training scenario, you are just evaluating, ahead of time that you just have to compute these outputs, and you would just be doing that. But if you had, let's say, a filter with 5 inputs over here, that would essentially mean that I would need a lot many more computations at each of the levels that is beneath it. If I were making that decision at a really low convolution layer, it wouldn't affect a lot of things. But because of the dependencies among the activations, it could lead to a...
You're right, you have to do two. It's like you partition the nodes into the set that's using the 2 inputs and the set that's using the 5 inputs, and then you do 2 different matrix multiplies.
Yeah. And the other thing we want to ensure is basically we need to have an understanding of which architecture to use both during training and decoding. So what you say might be true, that if I randomly switch the activations that are used to update this filter, I might actually have a more robust transform. But during decode time, I need to make a decision on what to use. So that would be an additional problem I would have to solve. I'm not saying it's not possible, but go ahead.
Did you have another question? Oh, the technical one, yeah. Why did, on the orange ones there, why doesn't it go to like, the pattern's irregular? It's almost as if it had gone in from both sides.
It's regular if you look from the top down.
Right. Look at it like a...
Yeah. So, or here the activations are being selected like this. At this level, I need a filter which, so the basic problem over here is dependencies in speech are asymmetric, left asymmetric. So I always need filters which have a wider left context. And this essentially means because of this asymmetry, there can be some non-uniformly placed samples. So the way we draw this chart is we select a particular filter and we try to decide, we basically decide what activations are necessary to compute the output of the top filter. And that's how this diagram works out. Mm-hmm.
No, I don't buy that, because I think the reason why it's asymmetric, or why you have this overlap in the orange layer there, is that because it's not a factor, it's not a power of 2. Your expansion, I think that is the reason, right?
So the expansion over here is basically a power of 3. So over here at the initial level, or here I have a filter which has a context of 3 plus 1, or here I have a context of 6 plus 1, and on the top of that we have a context of 9 plus 1. So depending on how exactly I am choosing.
Yellow circles there are 7, and if it were 8, then you would have a perfect binary tree here, right? So my question is...
So they are actually 8, it's just that I'm sharing one of those computations.
Yes, and that's my question. Is that necessary for accuracy, or is that simply
No,
because you
so-
somehow need to map it,
so-
you need to do something with that?
Empirically, we found that it doesn't matter what exact structure you are using as long as you are ensuring the propagation. So over here, it just turns out that because of the indices I chose an indices of -7 and 2 at the top layer.
Yeah.
Instead of that, I could have chosen -6 and 3, and this would be like a perfectly uniform, at each level, the nodes would be uniformly placed. So it turns out that these independent small changes do not affect the performance to the great extent.
So it would not make a difference, for example, if you put the one set of inputs that are used multiple times, right? You mean the middle node on the yellow layer there is used twice, it goes up through paths. Would it make sense to make the one that goes up through 2 paths to be the current frame, the center frame that you're predicting? Which it isn't here, right? Because
Or here it isn't.
seems you're over-representing a little bit of left context that doesn't seem to be warranted. Right?
Yeah, there were other subsampling methods where we always ensured that the center frame is present, and in order to reduce the parameters, we do use other tricks when we are taking context from. So we would just take a subset of hidden nodes, and whenever you ensure certain things, like you ensure that there is a center frame. And or if you think the left context is important, you would always ensure that there is more representation from the left context. You do get better performance.
One more question to Jeff. Are interview questions covered by NDA? Do you think the dropout idea you just had is really good? We should patent that.
I think they are.
So the big advantage, so these are the actual computations that you would do in this convolutional neural network. So by the way, another thing I want to make clear is, over here, because we want to actually compare convolutional architectures and recurrent architectures, we are not talking about convolution along frequency, but just along time. So we actually have affine transforms which are operating on the entire feature vector at a given instant, but they are just, these affine transforms are being shared across time steps. So over here you can see that there is a drastic reduction in terms of the actual computation that has to be done, but we still have to see whether this drastic reduction in terms of the number of activations that are computed, is it going to affect our performance, which I'll discuss later on. And it turns out that using this particular subsampling strategy, we were able to gain up to 5 times speed up compared to a normal TDNN without any form of subsampling. So in order to test out the basic setup, we started doing experiments on the switchboard LVCSR task, just the 300-hour subset version. And I'll briefly describe the setup just to ensure, because I'll be using this particular setup at several places in this presentation. So we basically use a 40-dimensional MSCC representation, which is essentially a filter bank, but just with the DCT transform. And we do that because we want to reduce the bandwidth usage when we are transferring data across nodes. And in order to do what is termed as instantaneous speaker adaptation, we append a 100-dimensional I vector for every time frame. And one of the main focuses of the technology that we develop is that we want to ensure that this technology is always ready for online decoding. So all the I vectors that are being used over here are just estimated using data that has been seen till that position in the sequence. And most of the systems that we use over here are trained with cross entropy. Whenever there is sequence discriminative training, I'll mention it specifically. Almost all these experiments were basically done using the CALD-ASR toolkit. And we use the distributed optimization technique where we do model averaging across instances. And yeah, so as I said, one of the goals was to ensure that we always had a really good online setup. And it turns out even when we are doing online mean variance estimation, there is a certain amount of latency, which is not necessarily due to the model, but just for the mean estimation. So we just wanted to test out whether there was a way to eliminate any kind of mean variance normalization and ensure that the network learns it, whatever is the necessary normalization. And when we estimate our I vectors, we estimate them on non-mean variance normalized features. So if there is any mean offset, it is encoded in the I vector. And it turns out that by using our training recipe, the network is usually as effective as a network which doesn't have, which has mean variance normalization. When we use,
you need to introduce latency if you want to estimate I vector, right?
Yeah, as I was saying, over here we ensure that the I vector is always estimated using data seen till that particular frame. So if you have a frame at 10 samples, only the data up till that frame is being used.
It's an online I vector. Online I vector.
So I do not claim that this is better. It's all towards the same goal that we want a really fast online system which doesn't have any latency, which is not absolutely necessary for the model.
It just seems that not having this sort of gain normalization that you get from mean subtraction is.
So in order to tackle that problem, we have other solutions. Yes, that is a really good question, because it turns out that most of the training, so if any kind of gain difference was there, if it was well represented in the training data, our model would be robust to that. But most of the training scenarios that we have are using well-curated databases where the gain is perfectly normalized. So we do see a lot of issues. And in order to tackle those problems, we do perturbation of our data. And as soon as we do that, we eliminate most of the issues.
So when you're training a neural network, the mean variance normalization also helps with the stochastic gradient to converge better. So you're giving that up. How do you deal with that?
In our case, we don't actually see problems like that. We haven't found any issues, either because of the nonlinearities that we are choosing.
Whitening, isn't this natural gradient stuff in there?
Yeah.
Does that help?
Oh, so I cannot make the claim because I haven't tested it out. But there is one additional phase over here that, yeah, there is nothing explicitly done to tackle this problem.
This is mean variance normalization on utterance scope or on speech scope, but I think what you're talking about is on corpus scope that is completely independent of that. You can still do that, and you will not lose anything because that only affects the training. It's not something you're estimating during the code.
Yeah. So
are you doing?
No, there is also no global mean variance normalization.
So I remember Dan's paper, they said the number 2 actually has some kind of close to the natural gradient species in order to do model averaging.
Yeah.
So is it because of that?
We haven't tested it out.
So your baseline doesn't have, let's say if you run standard with one GPU, you don't do model averaging, you don't have baseline number. This is your baseline.
Yes. So what we see is if you basically run it on a single GPU, you usually get better performance rather than distributing and doing an average. But the performance hit is not very drastic.
What's the number? acceptable margin?
We haven't tested it out, but in the cases that I did see, I would basically get something like 0.1 or 0.2% difference on switchboard 300R subset. So we don't usually worry about that.
The P non-linearity is not sensitive? What is that?
So here the p-norm nonlinearity, we basically, in the feature hidden activation vector, we select groups of 10 units, which are basically contiguous sets of 10 units, and we take we take some norm of it. In this particular case, we were taking the L2 norm of these activations. So these groups do not assume any kind of location, spatial locality or temporal locality. We basically select some set of 10 units in the hidden activation vector and perform the norm. And this was basically seen as a generalization to the max-out nonlinearity that's normally used. So these are the first set of results that we had. So let me guide you through this table. So the initial comparison that we wanted to do was, given the same amount of context that we normally use with a DNN, are we going to see any kind of advantage if we had a TDNN architecture? So in this particular comparison, I am taking the actual context of 150 milliseconds, which is being modeled by a DNN, and distributing across 3 different convolution layers. So I have a convolution layer which has a context of 4, 4, and 7. And it turns out that even with this distribution, there is an appreciable gain. But this comparison was not exactly fair, because as soon as you start using a convolutional architecture, there is a certain amount of parameter increase. So we conducted another experiment where we ensured that the DNN had the exact same number of parameters as the TDNN. And even in this case, there was a certain amount of increase in performance. And after this, we basically, the main goal of this set of experiments was to actually see whether we can model longer sequences using the TDNN. And because in order to test that out, we started modeling wider and wider network contexts. And it turns out that using the TDNN, we were able to model contexts up to 230 milliseconds in this particular closed talk telephone speech case. And when later on in our experiments, we identified that this also depends on other hyperparameters of the network, like the nonlinearity, but the interactions are not clearly understood. So I'm not bringing that into the comparison. So using the TDNN, we were actually able to model context up to 230 milliseconds. And once we did know that this context was helpful, we actually wanted to make sure whether the DNN could also do this. And it turns out, as we expected, that anytime you increase the context of the DNN, constraining the amount of data that you have, which is 300 hours in this case, there is always going to be some kind of detriment in the performance.
1, 2, 3, 4, 5, 6, 7, 8.
So
each of which could have like 3 or 4 values.
Yeah, and across all these values, we really don't see a variance in our performance. The one thing that we select is this. These are not hyperparameters which have so many degrees of freedom. So we initially select the first layer context that we want, and this essentially determines the context of the other 2 layers. All that we want is to adjust the offsets, and the adjustment of the offsets depends on the input context of the network that you want to model. So if you want to say model just 10 frames to the right and 350 frames to the past, the selection of these contexts would differ. And the other thing that we need to select is the number of convolution layers that we want. And that is usually a decision made upon how many sequential steps are you able to tolerate while you're training.
No, you don't want to do it. I'm not going to go deep, but just as a ballpark, the value, like what's the best? So it sounds like the value number is better than these. Just what's the best? Remember off the top of your head what's the best result for value?
So if I remember right, there was like a 0.5% difference on the switchboard, 0.5%. Yeah, on the absolute, on the switchboard subset. I mean, it was better, but not significantly better.
Question. These tables indicate some symmetry between the DNN and TDNN, because you use curly brackets and square brackets and so on. So is the first layer of the TDNN, is that already convolutional or still dense? The first, the -2 to +2.
That is dense.
That's dense. The first one is dense, and above that.
Yeah. Because the first one has to be dense because you have to span everything in the initial sequence.
You always use the same filter. Max pull that.
So the reason we want to do that is because we want to propagate the information from every time step. So that's the reason we have to make the very first filter dense.
But they're not tied.
Everything is tied.
Oh, okay, that was my question.
So like, so all those yellow 5
everything that
things.
is represented with the same color is computed from a tied transform. So it's if it's represented with a color, it's computed from the same transform. So all yellow outputs are computed.
All yellow nodes show the same verb.
Yeah. Sorry. So at this point of time, we basically wanted to compare our TDNN model with the state-of-the-art results on the switchboard at that particular point of time. And in order to do this comparison, we started adding a lot of bells and whistles to our baseline model. And one of the first things we did was basically adding pronunciation probabilities. So pronunciation probabilities are basically, once you have the lexicon, which has multiple pronunciations for every word, and you have your training data, after a certain amount of training, you basically realign your training data using this lexicon and see what is the probability of each pronunciation. And the next thing we did was basically a simple 4-gram rescoring. And after that, as I said before, sorry?
I'm wondering what speed perturbation, volume perturbation are.
Yeah. Tell us.
Yeah, so as I said before, we are always interested in online technology, so we do not do any kind of speaker adaptive training of our system. And this essentially means that we usually take a hit in terms of performance. And in order to compensate for this, we basically present the same audio data to our system while simulating synthetic speakers. So normally, in order to simulate the synthetic speakers, people have been doing a vocal tract length perturbation or tempo perturbation. But it turns out that both of these can be done using a simple signal processing operation, which is basically compressing or expanding your signal. Whenever you do compression, you are perturbing both the tempo. And because this compression modifies your frequency coefficients, there is also a perturbation in the MFCC coefficients.
So you're hacking the sampling rate, you're not just changing the frame shift.
No, we are hacking the sampling rate. Yeah. And this, one of the biggest advantages of this speed perturbation technique is that it's agnostic of your feature representation that you're using. And it turns out that that's a very critical decision for many people who want to use the techniques in different systems.
Following up on Frank's question, so you're saying that you basically sometimes pretend that you're sampling at 8 kilohertz, sometimes at 7.5 kilohertz.
No, so you can think of it, so we sample it at different rates, but we always assume that the sampling rate is 8 kilohertz. So that essentially means that you are either, that gives you the stretching or the compressing effect.
The equivalent to that, you add the synthetic data,
Yeah.
SP plus VP combined.
Yeah.
Okay.
So the volume perturbation is the thing that actually helps us tackle the mean gain normalization issue. So we basically train our system using several different perturbations of the volume, and and the volume of the entire signal. So the gain. Yeah.
Three-dimensional volume.
Sorry.
I still don't understand. So now you just said you always assume it's 8 kilohertz. So
Yeah.
but that's you're not just
So basically, if you have a signal at x of t,
Yeah.
you now want a signal at x of alpha t, where alpha is some number.
Okay, so
And in order to,
that is maybe like 7.5 kilohertz, and then you just resample it back to 8 kilohertz and run it through the standard pipeline.
you need not actually. So
Yeah, so
as soon as you resample it at 7.5 and pretend that it is 8 kilohertz, you have the compression effect.
okay, so
You
so
get-
did you evaluate that separately? I'm sort of curious
Yeah,
whether
so
speed and volume
there
are very
is a
different
paper
things.
last interspeech with that, and it turns out that across several different data sizes, we tested data sizes up till 1800 hours. The usual gains are 6 to 7% relative when we do speed perturbation.
And volume is about the same range?
Volume perturbation, in most of the tasks that we have over here, both our training data and test data are very well curated. So you don't see a lot of gain. But there are other tasks that I will present later on, where that essentially led to almost 15% relative gain. Because in that case, the gain differences in the test data were several hundreds of dB.
That's 15% you lost before because you didn't do normalization.
Yeah.
Okay, good.
So that's the
Sure.
reason. Yeah. So the basic idea over here is try to do as much as you can while you're training to ensure that your decoding setup is as online as possible.
I have a question. Why? I mean, I think it's great from the steal your stuff approach that you took all this online approach, but sort of, I mean, at a high level, I mean, as a site trying to win a challenge without that constraint, why impose that constraint?
No, so as I told, I also have some results on the challenge. And when we initially started with the challenge, if we were constraining ourselves to be online, we were basically taking a 10% relative degradation just because we were imposing the online constraint, either when we are estimating the I vectors or when we are not doing any kind of normalization of our data.
Why would you do that if you want to win it down?
So because of the challenge, because of the benchmark, we had to relax the challenge. But the online thing is just like a broader goal that we want to achieve. So any technology that we are using, so we don't want to invest a lot of effort in doing speaker adaptive training where we require 3 or 4 passes on the data. So then we added what we call silence probabilities. So usually when we have the silence occurring between, the probability of silence occurring between 2 words is assumed to be uniform in a normal lexicon. But or here we wanted to ensure, bring about the idea of the context of the silence impacting the duration or the probability of the silence. And it turns out that though the gains because of this silence probability estimation are not very high in this particular case, when we go to robust speech recognition tasks, we get significant gains because of that particular thing. And in so if you have the probability of a silence occurring after any word, normally it's assumed to be uniform. But over here we are varying the probability of this silence depending on the previous and the next word.
Word. So it's like a language model, sort of.
Yeah.
How do you train that?
So basically this was work done by one of my colleagues, Gogo Chen. So over here, if we actually are introducing all these additional arcs in order to model all these different silence probabilities, you have a V-square increase in the number of arcs depending on the vocabulary. So he basically partitioned this probability into 2 different parts where you try to see what is the impact just because of the previous word and multiply it with the impact on the next word. And it's basically modeled as an independent probability, and there are several tricks over there in order to ensure that it's actually easy to implement. And on the top of that, we did sequence training. And further, we did, there is one minor adjustment over here. This is not, this is sequence training, but on the top of that, we do something called prior adjustment. So this was something which was found by one of my colleagues called Vimal Manohar. When he was doing semi-supervised training with neural networks. He identified that after sequence training, when we want to estimate the likelihoods, instead of computing the prior based on the alignments, if you use the prior which is estimated from the mean posterior of the network, if you use that as the prior, it gives a lot of gain. And over here you can see that this gain is consistent. And it turns out that after his finding, we started using this trick across a variety of LVCSR tasks, and we saw consistent gains across all these tasks.
It made things worse. I had it in the DBN.exe tool from the very beginning, and I switched it off because it didn't make things better.
Okay.
Interesting.
But that is only for CE training.
Yeah, right.
Yeah, but this one is for sequence, might be different.
Oh, right. Excellent. Okay.
So at that point of time, these were the papers with the best results on the switchboard 300-hour set. And we do see that we are definitely able to perform better than the unfolded RNN implementation by George Saon. But this is definitely not a fair comparison or even a proper comparison because the setups differ in a variety of ways. So later on, I'll give a comparison between the TDNNs and the LSTMs, which share a lot of same things.
So the bottom line seems to be that with a well-trained single system, you can get down to like 11%.
Yeah.
With the 300-hour data.
Yeah.
And when you start combining things, you can get down into the tens.
But there's no, your system does not have.
This system also has speaker adaptation, and the I vectors are offline estimation. This is one single I vector per utterance.
Are there I vectors in the TDNN?
Yeah, sorry, I didn't explicitly. I already mentioned that they were used in all the systems that
The incremental ones.
Yeah, the incremental, the online I vectors are used in every system that I present result on.
So the bottom line, does that have RNN?
This one? No.
Yeah. No.
So I'll show you results with RNN later on.
How much did the I vectors give you?
So I vectors usually give us across stars around 7% relative, but if we go to far field recognition tasks like ARMY or the other tasks that I present here, we get bigger gains.
In the incremental fashion.
Whenever we do, even in the incremental fashion, we see gains. But if we turn off the incremental thing and start doing offline estimation, the gains get slightly better. So once we did see that we were getting improvements because of the TDNN models, we started testing them out on LVCSR tasks of different data sizes. And we found that across all these tasks, which have data ranging from 3 to 1800 hours, we do get 5 to 7% reduction, relative reduction in word error rate. There was just some discrepancy in the resource management task, but we didn't do a lot of tuning on that. So these gains were consistent, and because of this, we started using the TDNNs as the standard DNN recipe in the CALDI toolkit. So now the comparison between the TDNNs and the RNNs. So after that paper was published, we actually wanted to compare locally what were the best RNN numbers that we could get. And it turns out that despite the claims of having the best TDNNs being able to tackle long-term sequence dependencies, they were still performing worse than an LSTM. So over here I have numbers on a switchboard task, which is the telephone speech task, and the ARMY single distant microphone task. And in both these cases, you can see that there is a degradation because of switching from a RNN to a simple convolutional architecture. And so that is one of the efforts we are doing right now. So over here, you can see that the best numbers that we have over here are because of a bidirectional LSTM. And this brings inherently a lot of latency into the model. Even if you do chunk-based training, there is a lot of computational overhead because you would have to compute the right state of the model. So right now we are looking at efforts. I'm making an effort where the right context is being modeled using the left context is being modeled with an LSTM, and the right side context is being modeled with a TDNN. And I'm trying to. Okay, so. So the right side context is being modeled with the TDNN. So the essential idea is if you want 20 frames of context to the right, rather than directly dumping it into the previous model. So right now the trick people use in order to model right context with LSTMs is basically predict a label with a delay. So you would go update the state of your LSTMs for 5 more time steps before you predict output. So right now we are trying to combine these two things and achieve the performance of the BLSTMs.
Another way, which is, in the workshop, actually, we already have the results, which is go back from the right context, using the recurrent network, go back to the central place you want to predict. That can also model the right-hand side context with limited latency.
Yeah, so that's the chunk-based, so that is similar to the chunk-based training, if I understand right.
Slightly similar. Yeah. Not exactly the same, but.
Yeah. So that's the reason. So over here, if you actually use TDNNs, most of the activations that you compute for your right context could also be reused. So in that particular case, you would have to redo this propagation step every time you do a shift.
No. So the left-hand side context is completely modeled with normal unidirectional LSTM. So you carry over all the history information. You don't do truncation. Only the right-hand side is doing truncation.
Okay. So if you want to do it for a new chunk, you would again redo the.
Only the right-hand side.
Okay.
Yeah. Left-hand side, you don't do anything.
Is there a analogy to be in LSTM to sort of? I mean, so you were able to in your model, you basically reduced a lot of the interframe correlations from your model. You basically have these big skips. So you can imagine an analogy, and LSTM would be
we do,
not every sample.
So these LSTMs actually do that. So in these LSTMs, we do not just do a recurrence to step of -1. So the lowest LSTM has a recurrence of, let's say, a step of -3. The LSTM on the top of that has a step of -6. And the one on the top of that has a step of -9. So if you unfold this model, you can see that we are not taking the states from all the lower layer outputs. It actually improves over the performance. So this is the LSTM which has that.
So that's a separate thing. You're marketing yourself. Just show the vanilla LSTM.
Yeah, where is the vanilla? Is it
so
similar to
the deviation is minor.
Oh, I see.
It's not substantially different. But the main reason you would do that is because you would get speed gains when you are doing sequence level objective training like CTC.
What code did you use to implement the LSTM or the LSTM?
So those are Kaldi code. That's the reason these are like later results which are done after the paper.
So question about the TDNN results. So you said earlier on that by doing the subsampling trick, you don't lose anything. Is this confirmed on switchboard, or did you evaluate that on other program?
So I didn't make the claim that I don't lose anything. I still have to verify that, and I have experiments which do verify that.
Here's where you would be, where this 12.1 number would be if you didn't do the subsampling.
Yeah,
I
actually have that.
I think the gap's bigger than I would expect here.
Yes. Mm-hmm.
And you don't have the number.
In the later slide, because that's still preliminary work. I don't want to make the really strong claim using that.
By the way, so what's the reason you think LSTM still performs better than TDNN, even if you can look at larger context?
So with the TDNN, there is this additional hyperparameter which we have to adjust, which is the amount of left context that we need. And this is usually done empirically, and as I discussed before, there are a lot of interactions in the model. When we switch the nonlinearity from a p-norm to a ReLU, it turns out that we could actually model a wider context. Rather than just going till 230 milliseconds, I was able to go till 300 milliseconds. So this additional hyperparameter tuning brings in a lot of issues. So assuming that we still have a really, because we still had a really fast TDNN. So in this particular case, I would like to make a comparison of speed between the TDNN and the LSTM. So here the TDNN is 3 times as fast as the LSTM. So because we had this really fast model, which was still able to tackle context of greater length. Sorry, go ahead. Sorry.
What about an LSTM that is 3 times faster, for example, that has 3 times less model parameters or whatever it comes to?
So over here, all these models have similar number of parameters. So there is not much difference in terms of the number of actual multiplies that are being done. We are just doing them parallelly or sequentially. That's the major difference.
I'm still curious how an LSTM will perform that is as fast as the TDNN. I always vary about these comparisons about parameters equals.
Yeah, I'll test that out. The last time I gave this talk over here, Jeff made some suggestions, and that did lead to some improvements. So I'll definitely test that out. So given that we had this subsample TDNN model, which was operating very fast and at the same time doing a lot of, which was able to train on a lot of data, we wanted to test this out in the far field recognition task, which is known to have a lot of sequential dependencies in the data. And why exactly is the far field recognition task so bad in terms of dependencies? It's usually because of the late reverberations. So late reverberations are reflections of the actual signal, which happen after 100 milliseconds. And usually the late reverberations are non-stationary. So noise robustness techniques which assume a lot about the stationarity, or which do not assume varying sources which are moving, are very difficult to apply when we have reverberated signals. And the other problem is late reverberations is they are the actual speech signal which is being added to the speech signal. So you can assume that they are very correlated with speech. But in most of the normal techniques, people assume that these are not correlated because there is sufficiently long delay between the actual signal and the reflection. But that's still an assumption. So if we want to tackle late reverberations, you can immediately see that any model which has ability to model wider context might be able to learn invariant or stable representations when we have these. So that's why we wanted to test out the TDNNs in the far field recognition task. And we decided to participate in a challenge which is called the Aspire challenge. And one of the qualities of this challenge was very beneficial to us. And that was, there was a well-defined mismatch between the training data, the dev data, and also the eval data. So the training data was just clean telephone speech, 1800 hours of Fisher data. The only information given to us was that the test sets are going to be with reverberation. There was no kind of metadata supplied. The dev data that was supplied for us to test out our models was ensured to be sufficiently different from the eval data. So in the eval data, there were greater number of rooms, different microphones, different types of different speakers, and speaker microphone relative positions were very different. So this was a really good task to test out a model which can train on a lot of data. So these are the sources of variability, and these are the typical room configurations. If you are interested, I can discuss further. So let me play out some samples from this particular task.
You should. There's a blogger who started when he was like 11 years old, 10 years old. He's a video blogger. I think it's called foododdities.com, and he just.
So that's the typical example that Mary Harper, who conducted the challenge, want us to play. So this is the lowest error rate that we had with the model, per speaker error rate, which is 26%. And this is what it sounds like.
Huh. Yeah. It's interesting. I actually just recently found out that like some of those weaves are actually real hair. Like I didn't even know.
So you can see that the data is very easy for humans, but very difficult. Yeah. Yeah. So it's easy for humans, and we had a 26% error rate with our ASR system. Now the third one, it's still very easy for humans, but we started getting higher error rate.
Hi. How's it going? I'm good, I'm Dave. Yeah, we've talked before actually. Yeah, I don't. Yeah, I don't know.
So this was a really hard sentence for us because we started getting a 41% error rate, though we were able to. So I initially thought maybe it was because of the keyboard clacks and started verifying the actual hypothesis, and that was not the reason.
That low frequency hum that's in there should not affect your recognition because you use telephone filters, right?
So I'll actually describe the training data setup. We use a lot of multi-condition simulation in order to simulate reverberation, noise settings, and a lot of other things. So it's not just
a specific thing. Are you using the full bandwidth for the MMCCs that you're extracting, or are you using a telephone extraction?
No, yeah,
that's normally what you go to for. So then this should not affect you, right? This low frequency.
This particular thing, no. Yeah, because there is a lower cutoff.
Yes.
And this was much harder for us.
Hey, how you doing, Sam? Oh, I'm hanging in there. I try to, stick to the topic.
So,
there's actually speech to that.
Yeah, there is speech in there. And the basic problem out there is if we were applying gain normalization techniques, they would have actually distorted the signal a lot more because there was a close noise source, which was the actual microphone moving, and there was the speaker in the background. So a simple. So this is the one I played. So the second last one.
Hey, how you doing?
I'm playing the second last one again.
Oh, I'm hanging in there.
Yeah, that was one of the papers.
I try to, stick to the topic,
Yeah. No, if you have a really good headphone and listen to it very carefully, you start. So it turns out that we had to amplify the signal several times before we actually heard it.
Exactly, the 40% accuracy for this?
No, it was 60% error rate.
Error, I know.
Yes.
That's human. Human can do that well at all.
Yeah. And so this was one of the things which was very tough for us. Our ASR never generated any output for this signal. Sorry?
So this is synthesized data, right?
Sorry? No, this is the actual data. This is data. These are samples from the dev data that they gave us.
This is real data, not synthesized. The dev set is real data.
Yeah, the dev set.
So how the human can transcribe those?
So over here, for that, if you were doing a really good gain control, you can actually start listening to the humans.
So how much is this kind of data are in the training set?
So the training set has absolutely no data.
There's no
because training data is just telephone speech.
just really.
So we have to do a lot of simulation of
So
these
you have
things
to add
in
the
the
noise to simulate it.
But this is just doesn't make a lot of sense. If people have all kind of recognize, why do you actually make your life harder? Just for the fun?
Yeah. So these were the samples. So this was the challenge.
Throw away the data. This is just normal people cannot even transcribe anything.
This is also just telling them where and where they shouldn't put their listening devices.
So if you think that is worse, you should probably listen to this. So all that I could make out was that there was a female speaker.
People in this room to transcribe, you get 80% errors. So
that's why I
you wouldn't pass the human parity.
I heard.
Yeah, they are human parity already. Because they're all bad, equally bad.
So zero output is equal to human parity.
0.
Yeah. So those are the kind of samples that we were dealing with when we were starting with this challenge.
Here, there's a speech there.
Yeah.
But the one before that, I couldn't even tell the speech there.
So for the one before that, if you had gain control, you will start here.
Gain control. But last one, I heard she's saying she's great or something.
Wow, you're actually able to make out more than any of us could.
You way better than the last one.
So we have about 20 minutes.
Okay, yeah. So or here you can see that there is a lot of mismatch between the training and the test data. So our only solution to this was basically collect as many room impulse responses that we could find open on the internet and try to distort our data using all these impulse responses. And if there was any corresponding isotropic noise along with the impulse response, we would also add that to our data. So doing this, we basically created 5,500 hours of training data. And in order to tackle the late reverberations, we just thought using our TDNN would solve the problem. So these are the first set of results. So in the top section of the table, the comparison is between a normal DNN and a TDNN. But over here, we are not doing any kind of simulation, distortion simulation in our training data. And you can see that the error rate is 47%. And just by adding all these different kinds of reverberation, we get a 37% relative gain, and which is quite drastic. And even there were even other sites which saw similar gains. And sorry. So we basically increase the amount of training data 3 times by doing choosing different pairs of room impulse response and actual speech wave file. So,
what was your relative improvement from TDNNs on the clean data before, or on
before it was 5 to 7%.
7%. So you cannot really make the claim that TDNNs give you specifically a great gain in the presence of reverberation.
Yeah, we can because of these 2 columns. So when we do match the training data, and when we do different kinds of distortions, the performance of the DNN is at 33.1%, and that of the TDNN, the best TDNN that we could get is 30.8. Yeah.
So if it already, even in the clean speech, you go from DNN to TDNN, it also gives you 5 to 7%, then you can't really say that.
No, I'm just saying, making the claim that there is an improvement and there is a sustained improvement. I'm not saying that in this particular case the model is going to be far better.
Right. It's not. You're saying.
But also you have to
specifically address it.
Because you can argue that the TDNN is specifically suitable for addressing the long-range dependency, but now, I mean, you get 7.
So the problem out there is that long-range dependencies are existent in all ASR scenarios. They are just more predominant in far field recognition. So, and also there is other change over here that the amount of training data increased from 300 to almost 5,500 hours. So using this larger amount of training data, the DNN could have solved some of the issues.
Yeah, you can argue. Could actually also benefit.
Yeah.
Maybe more.
Yeah.
But you don't know, do you?
No. At that point of time, we did not have a local implementation. And it would definitely have taken a lot longer to train using the LSTMs, and training time was the most critical thing over here because most of the gains that we were getting were because of simulating the data. So the most significant gain over here is the 37% relative gain, which is just seeing more amount of data.
So if you, instead of doing 3x, you're doing 30x. Yeah. Have you tried that?
Not yet. So this was the maximum. So after doing this experiment, most of the people in my lab started hating me because I was taking all their GPUs. So sorry.
You do not have enough GPUs, that's why?
We have 50 GPUs, but I was using all of them for a period of 2 weeks, and everyone hated me. So I couldn't do any more experiments after this.
Actually, it's 30x, your error is 3%, that is worth it. Right?
Yeah.
Hey, so how many GPUs did you use in one training run?
So in this training run, we use 32.
In one run? So you do model averaging over 32?
Yes.
Oh, okay.
We had to do that because we needed the output. And even with that, it took us 3 days to train. So
That's
and
not bad.
you're still confident that the loss is only 0.1, 0.2%?
No, I'll show you.
Okay.
So, yeah, we do not make, I did not make those comparisons across every task. It was just on very specific tasks that I did see modifying how the number of jobs affected the results, and it was always in that range.
Even if you go back the large number of GPUs.
I cannot answer that question because I never attempted a comparison. Yeah. So one other interesting thing we saw was when we were using TDNNs in far-field recognition, basically longer and longer context helped. And when we go to very specific tasks like Army, we saw that we were even able to model context up till 500 milliseconds using TDNNs. So let's take a look over here at various things that we did. So this was our system that we submitted to the challenge. And after the challenge, we started adding other things like RNN LNs, and we were still able to improve on the results. But this is the result that we were comparing with the other sites. So in all the sites, you can see that the results on the dev tests are similar. But when we look at the result on the eval set, which is the actual comparison being done, you can see that there is a drastic increase, almost 57% relative. When we and that is just because of the greater variance in terms of the eval test set that we had. So this shows us that mismatch of data is still a problem, despite us having a free rein on what we could add to our training data. There was still a lot of unseen data that we could not deal with. Even with the dev set over here, we were getting good error rates, but we did not even select the room impulse responses based on the dev set data. We did not use any metadata information when we were doing our room impulse response selection. So I'll just briefly discuss some of the ongoing work. So let's come back to the same slide, which is a comparison between LSTMs and TDNNs. So to answer your question, so when we have TDNNs and when we are going to use them with sequence level objective functions, where we are going to compute several outputs simultaneously, you can see that we are actually going to use compute several intermediate activations. Though not for the current output, you would anyway be computing for them for the next output. So it's not actually necessary to increase the subsampling rate at such a exponentially decreasing scale. So over here, you can see that in order to compute the first gray output, you are computing the time step over here. And in order to compute the orange one, we are anyway going to shift, right? So if we are going to do this, the cost of computing the intermediate outputs can be basically distributed over the entire chunk on which we are doing sequence training. However, if we actually want to use all these outputs, we still have the linear increase in the number of parameters. That still remains a problem. So in order to solve this problem, we decided to explore pooling options. So basically, if we had a filter at the next layer, which was just using 2 outputs, and we wanted to use all the data, we use different kinds of pooling at the lower level in order to reduce the sampling. So we tested 3 different kinds of pooling, which is basically using a 1D convolution, which is either fixed to be a smoothing filter, or a filter which is learned, but which is common across all the feature indices. So we basically have a 1-dimension convolution filter, which is shifted across feature indices, or basically using a different filter for each feature index. So these are the results. So these were the results with the original cross entropy objective. There was a difference between subsample TDNN and the LSTM. And this is the same subsample TDNN, which has this exponentially decreasing sampling rate as we go deeper. But if we increase the sampling rate and ensure that the subsampling rate is same at all levels, so if we just fix it to be 3, we do see a slight gain. And when we remove the subsampling completely and use all the frames, but decrease the parameters using pooling, and when we use per-dimensional filters, we do see significant gains. So to answer your question, there is a detriment because we're doing subsampling. But if we wanted to do the same thing in normal frame-based, frame randomized training, there would have been an increase in training time by almost 5 to 10 times, depending on how.
The LSTM only gained 3% less than 3% relative from sequence training.
Yeah. So as I said, these are very preliminary results which are just from last week.
I see.
And so Dan did some debugging, and he did find out that there were very specific issues in using the sequence level objective with the LSTMs. And right now we are trying to rectify that. And we do hope that the LSTMs would give us slightly more benefit. But the main thing that I wanted to highlight over here is that removing the subsampling actually helps. And there is a slight gain between the original TDNN that we had and a TDNN which is making use of information at all the inputs. And this comes to us without any additional cost because we are using a sequence level objective and we can share the computation across the entire chunk. So assuming that we do finally, sorry?
The last one that at decode time is still run as a non-subsample model?
Yeah, even at decode time you always have chunks, right? So it's always a non-subsample model. So even before at decode time we did not gain a lot because of the TDNNs because you always have chunks. So assuming that we are able to improve the performance of the LSTMs, there would still be a gap in performance between the TDNN and an RNN model. So we started looking at ways of actually taking an RNN model and trying to improve its performance to the level of normal LSTM while ensuring that it had all the multi-rate nice properties that we want, which is really low training time. And it turns out that one such RNN already exists, which is basically called the Clockwork RNN. In the Clockwork RNN, let me briefly describe what it does. So rather than just having a simple recurrent unit, set of recurrent units, you partition the recurrent units into individual groups where each group is running at a different clock rate. So some of the recurrent units are just being updated once every 2 time steps, while some are being updated once every 4 or once every 8 time steps. And one other peculiarity about this architecture is that there are always connections only from the slow units to the faster units. So here I have a set of units which are operating at R/4 Hertz, and these just have connections to R/2 and R/1. There are no connections from the faster units to the slower units. So what does this actually mean? So this is a typical recurrent computation that you have. Over here, each block corresponds to one partition of the matrix, and each color corresponds to a particular sampling rate. So if you have a normal recurrent equation, you would have a full matrix over here. And instead of the full matrix, you are partitioning the matrix. Over here, white means there are no parameters. There are no parameters because there are just connections from the faster units to the slower units. So if you are computing the fastest rate output, you are using all the partitions from the slow rate outputs. But if you are computing a slow rate output, you do not want to use any parameters. So this essentially reduces the number of parameters by half, which is a good gain. And on the top of that, only this particular block is computed every time step. This particular column is computed every 2 time steps, and so on. So there is a really great reduction in the amount of computation that is going on, and also in the number of parameters. But these are not the main things that make this model very attractive. The biggest gain because of this model is that it improves the memory of the network. And that happens because the model is basically looking at input data at different temporal scales, and it has several different paths into the past, each with different delays. So this essentially Kotnik et al. Show that this model is very competitive and in some tasks is able to match or even exceed the performance of the LSTMs. So because it was so attractive,
what they study.
These are toy problems, and the only speech problem they had was word level classification. So we tested out the performance of this model on the speech task, and it was very bad. It was far.
So did this ever outperform anything?
I'll show you.
Okay.
I'll discuss some preliminary results. So on this acoustic modeling task, the performance was very bad. It was far worse than the normal DNN. And so we started making modifications. So one of the first things we did was there was subsampling happening in the network. So what is something every signal processing engineer would do? Have an anti-aliasing filter to ensure that there is a smoothing of information and ensure that information from all the time steps is used in the filter. The second thing we did was we removed the tan hyperbolic activations that were being used in the Clockwork RNN, and based on the experiments by Kwok Lee last summer, we started using rectified linear units and the diagonal initialization that they suggested. So as soon as we started using anti-aliasing filters, we saw a good gain. When we used rectified linear units, that was the major gain. And the diagonal initialization gives us a slightly larger gain, but which is not very consistent. And in order to reduce the output dimension, we just started using the fastest units, because in acoustic models, you are evaluating the output at every time step. We thought that only the fastest outputs would be sufficient. So all these gave us really good gains. And finally, we were able to substantially improve over the original Clockwork RNN. But the results were still just as good as TDNNs. I'm not presenting the results right now because the experimentation is not extensive, and I do not think I can make strong claims. So right now we are still looking at ways to improve the performance of the Clockwork RNNs. And one of that would be to just simply use the Clockwork RNN idea in any model that is already performing very well, which is using it as to control different gates in an LSTM. So the only thing over here is that whenever you have a recurrent matrix, you can partition the recurrent matrix. And there are a lot of models where you have recurrent matrices.
Is it possible, because actually the read is fixed, you have full read and then half and quarter and something. So I think the parallel LSTM is using gates, so it's automatically learning to control the flow of the different things. So I think this kind of read definition is kind of a problem in this clock part.
But you can see that it's not essential to always have a fixed set of rates. You could actually choose to evaluate these partitions at any rate that you want.
Why don't people do RNNs where the history state that you feed back comes from a CNN with max pooling? So sort of a max pooling over multiple history states. That should give you a little bit like a Viterbi-like alignment or something.
So that's what Jeff was suggesting before in the meeting, where you basically wanted different histories to be contributing to the state when you are making the current prediction. But in your case, you are adding the additional layer that rather than concatenating all these histories, you want to do some kind of pooling operation on.
Time alignment
exactly.
operation.
That would
Has anyone ever tried that? I don't know.
Maybe you should patent it again.
Seems very straightforward, actually.
Yeah, definitely. Right. So let me try to summarize what I did till now. So basically, we showed that multi-rate architectures provide us good gains. So the models by themselves are not powerful compared to their non-sampled variants, but the major advantage that you get because of multi-rate architectures is the speed advantage. And these speed gains can be trivially converted to performance gains by using more training data. And in many cases, like the Aspire challenge scenario that I showed, the most critical thing was seeing as much training data as you could. And this kind of these architectures give us really good way to do that. And another advantage, which I didn't talk about a lot in the multi-rate architectures, is that they operate on multi-scale representations. So in this particular architecture, the input vector that is being at this particular Clockwork RNN is being smoothed out. So as soon as you start doing smoothing, if you remember the very first slides I showed, you actually get these multi-scale properties, and the input representation over here is going to have this really nice distortion stability guarantees. And because I can do this smoothing at various levels desired, I don't not only have really fast architectures, but also architectures which can be really robust if I am able to properly get the training done. So this is one other reason that multi-rate architectures are very attractive. Even in the TDNN architecture, as we go deeper into the network, it was actually seeing lower and lower resolution information. So the other advantage of multi-rate architectures is that they actually have access to multi-scale representations. So if you want more details about the things that were discussed in this particular talk, you could go through our interspeech papers. Let me briefly describe the future work. So as I said before, the problem that interests me is the distortion stable sequence recognition problem, where you have long-term sequence dependencies and sequential distortions in data. These challenges are existed in all ASR scenarios, but these are very predominant in far-field recognition. So that because of that reason, after I was introduced to the far-field recognition problem by Mike during my internship over here, I started working in this area a lot. And this is one particular table. This was the state of our Kaldi Army recipe last summer before the JSOLT workshop. During the JSOLT workshop, we were able to work on the TDNNs and bring it down to some extent. And after the workshop, we started using stronger and stronger models. And we got up to 46.1% just using the BLSTM models. And even if you use a lot of other tricks like using clean alignments for training or using beamformed audio data, all that you can get is you could just move from 53% to 38.3%. So first of all, when you do anything on far field recognition, the gains are look significant. So it's very satisfying. But the other good thing about this problem is that despite all the things that we did, we were not able to match the performance of the closed-talk microphone system, which was this. There is a 69% relative degradation. And this is not ground truth in terms of human performance versus system performance. These are two systems which are exactly trained on the same data and same language models. The only thing that differs over here is the acoustic data. And that giving a 69% relative degradation. It's a really good motivation to work on this problem. So most of my focus recently has been in this particular case. So thank you.
I do have a question.
Go for it.
So essentially what you did, I want to describe it a little bit like you have applied AlexNet, this image processing pyramid to speech in a sense, right? Mm-hmm. So you're dealing the same thing that they do for translation invariants and so on. It's basically what you are doing in time direction. Right?
So those are already done in normal convolutional architectures. The gain that we see is we just want to also do this very fast.
So my question is, can you now go backwards? Can you take your subsampling technique and apply it to AlexNet? Because that's probably could give you, now you save in 2 dimensions, right? Mm-hmm. So you could give you like a square gain.
Yeah.
Yeah. But the performance-wise is worse. You can already show that.
Right, but the question is maybe the performance isn't that much worse, and so maybe you can actually get a huge speed up at the limited cost. If you want to run it on a mobile device or whatever.
Yeah, so this suggestion was made by Tara when I showed her this work. So she was suggesting actually using the subsampling technique both along the frequency and the time axis when you had the initial limits. I guess that's what you're saying.
Yeah, except applying it to image, right? Okay. That's where probably would get much bigger gains because you don't have 40 components but you have like 56 pixels or something.
Yeah.
But I can save it.
No, I had a question.
Oh.
Okay.
So you started out with this motivation of, so I guess there's 2 approaches of to tackle far field. One is sort of to try to address models that specifically address the distortions present in far field. Mm-hmm. And that sort of seems to be your motivation sort of carefully this time. And then there's this other approach to say, which is sort of this raise all boats thing, which is basically, well, we're just going to improve things that improve everywhere, and eventually the gap will still persist, but the gap will be so small that we don't care, right? So if we can get from 1% to 2%, if the absolute value of clean is 1%, the absolute value of far field is 2%, I will be happy, right? Then we can call it. So it seems like you started out going for option A, and you ended up in option B because you sort of had the same improvement across clean and distortion.
So actually, the timeline was a bit other way. So our initial goal was basically have an acoustic model, improved acoustic model which performed well everywhere. And it turned out that these acoustic models, because they were tackling very specific kinds of things, were working far better in the far field recognition case. So,
okay. But now what do you actually believe?
Oh, okay. So I think that ASR problem as such would basically if you guys do achieve the human parity in a few years, you would basically start relaxing the constraints in which you are recording speech. And I believe that there is no separate robustness problem or a far field recognition problem. There is basically speech recognition problem. And I guess any kind of acoustic model which is performing well would actually give benefits in a lot of these cases as soon as you start relaxing these constraints in which we assume that we are going to operate in. So to answer more specifically, so assume that you do have certain kinds of techniques. Let's say the techniques which work on raw speech, so which are showing slight improvements in terms of performance in the actual clean speech, telephone speech recognition case. These same techniques would actually give us far more improvements. And papers in the last interspeech and ASRU have shown that when we apply raw signal processing, signal models in far field recognition, you do get better gains than what you normally see. So I don't see a really strong distinction between these 2 problems. But I definitely think that even if you start just focus on the far field recognition problem, you would see gains on the normal problem.
So early on in your talk, you said, well, look, there's two ways we can approach the problem. We can try to make long span features and feed long span features directly into the system. Or we can have a model that somehow learns to characterize the distant past in the operation of the model and keep it in some hidden state and basically learn how to characterize the past. So do you have a sense now of which one is better? Like how would the modulation features do if you applied it to the same?
Let me slightly rephrase the question. So it would be, assume that we have the same architecture. Yeah. So recently there were a set of features called scatter features proposed. So computationally these are a convolution neural network, and the only difference is over here you are computing using fixed filters. So over here the filters are designed for you to achieve all these distortion stability guarantees that I was talking about. So you would have all these things, and on the top of that you would use whatever acoustic model you wanted. And the other way would be to basically make this a learnable model and basically tune everything. So there was a recent publication in December 2015 where people showed that in order to prove that your model has a particular guarantee, it's not necessary to restrict them to be learned design filters. So if you have a design filter, you have a lot of good understanding about what the filters are. You know that it's a wavelet which has this dilating Gaussian as you go to the larger bandwidths. But they showed that in order to make proofs about distortion stability or all these guarantees, it was not necessary to have this design. It was also possible with learned filters. And all that you wanted over there were these very specific characteristics in terms of the model design, which was temporally local or frequency local transforms in their case, or the convolution operation as such.
Are there ones any better because it's a lot faster to just compute some features?
So there has been a lot of effort in trying to learn this transform from raw signals, right? And over the past 2 to 3 years, it's only in the last interspiece that they were actually showing that the learned filters that they had were performing slightly better than MFCCs. But even over there was no guarantee that these filters were going to perform as well if there was a slight deviation in the training condition, a mismatch.
So I think the feature-based approach has one fundamental flaw. It's one thing that it absolutely cannot model that the model-based approaches that you suggested can. You know what I mean? Otherwise, we'll talk about it later.
The task-specific thing, the task-specific objectives that they can do.
No. One specific limitation that any fixed width filter or something is not able to model that you model very well.
People do acknowledge that fact. They do understand that in feature-based approaches, there is no prior understanding of what is very good for the particular task. They usually solve that problem by using several different kinds of features. So even if you are doing multi-scale approach, you would just not use a single filter bank in order to generate your multi-scale representations.
Okay, I think we're about out of time. Let's thank Jay again. Great talk.